right, let's do number 3. A fossil originally contained 6.5 grams of carbon-14, which has a half-life of 5,715 years, approximately. How much carbon-14 will remain after 1,000 years? And then the second question, suppose an 1,000-year-old fossil is found and it has 2 grams of carbon. We want to know the initial quantity of carbon-14 in that fossil. So this is 2 totally different questions. Well, not totally different, but so we'll look at part A, the first question. We want to know how much carbon-14 will remain after 1,000 years. Okay, so carbon is decaying exponentially, so it's an exponential decay, so it's very slow, but it's a continuous decay. So we are still going to use our decay equation. And it does not matter if you say that R is positive or negative. We know it's decay. We know when we solve this, R is going to be a negative value. So we can just use this equation here. Okay, so originally we had 6.5 grams. So that's our initial amount. So we know that. We do not know R. So we can't plug in 1,000 for our time and solve anything until we know R, our rate. But we can find our rate. Let's see. We know that we have a half-life of 5,715 years. So we know that if our time is 5,715, in that amount of time, the 6.5 grams of carbon will be cut in half. So we will have 3.25. So we're going to solve this and we'll be able to find out what R is, and then we can go back and solve the rest of our problem. So we divide both sides by 6.5, and we get 0.5 equals e to the 5715r. Our exponent has our variable, the r that we're trying to solve for is in the exponent, so what we're going to do is take the natural log of both sides so that we can use the down and front property. Just try to scroll this up so I have more space. So we get natural log of 0.5 equals 5715r, natural log of e. Of course, the natural log of e is 1, so that goes away. And to solve for r, we're going to divide both sides by 5715. And when we do that, we get r is 0.00012. So that is the rate of decay of carbon-14. So the question was asking us how much carbon are we going to have after 1,000 years. So go back up to our model. We know that we started with 6.5 grams. And now we know our rate, 0.00012 T. So we can find out how much carbon we have anytime using that. They want to know after 1,000 years. So 6.5 E 0.0012 times 1,000. And when we plug that all into the calculator, wait, R was supposed to be negative. Did I not push the buttons in my calculator right? Hang on. 0.5 divided by 5715. Yeah, I apologize. R was supposed to be negative. We need that. This is decay. Negative, negative. There we go. You're not going to get right things in your calculator if that's not negative. Okay, plug that into your calculator, and we end up with 5.76 grams. Okay, B. Suppose a 1,000-year-old fossil is found, so they dig up this fossil and it's 1,000 years, and it's 2 grams of carbon. We want to know what's the initial quantity of that. So, y equals a e to the rt. Okay, same equation. Let's see, the amount that we have is 2 grams. So when we dig this up, we have 2. And they're asking, what was the initial amount? What was A? R, we do know R because it's still carbon-14. We just calculated it. It's the negative 0.00012. And time, this is a 1,000-year-old fossil, so we're going to multiply that by 1,000. Hopefully I can fit it in there. Okay. So this is what we have. So we're trying to solve for A. So what you're going to do is you're going to divide both sides by e to that giant mess. E giant mess. Those cancel. So you're going to take 2 divided by e to the negative 0.00012 times 1,000. And when you do that, we find that this fossil started with around 2.25 grams. On the next page, we're going to do some slightly easier problems that deal with money. I don't know why money is easier, but it just is.